Hi students, how are you? I hope so you are all fine. Students, in this video lecture we will discuss about the example of the norm linear space. Most of the students are comment, sir please make the video on the norm linear space. Now in that video we will discuss about the example of the norm linear space. For all x belongs to r raised to power n, the elements of r raised to power n are like that x1, x2 up to so on xn, because r raised to power n is the n-dimensional space under the norm defined by, we have defined norm on r raised to power n as norm of x, which is equal to I from 1 to n xi square root is a norm metric, is a norm linear space. And we have to show that r raised to power n is a norm linear space. Now we prove it. Now there are three conditions to prove any of the space to a norm linear space. The first condition, norm of x must be greater or equal to 0, and this is the first condition. And the second condition is of x which is equal to a mod of a norm of x, and the third condition is the triangular property x plus y less or equal to x norm y norm. Now we prove one by one. Now we take the first condition, norm of x, take any element which belongs to r raised to power n and take norm. We have taken norm of x, which is defined under the metric I from 1 to n xi square root, where x belongs to r raised to power n, and b, remember the elements of r raised to power n like that x1, x2 up to so on. Here for any x belongs to r raised to power n, norm of x must be greater than 0. The reason is that x belongs to r raised to power n. If x less than 0, then it becomes complex, then it not be the element of r raised to power n. B, remember students, if x less than 0 means it is negative, and if the negative number is under root, then it becomes complex. Here the elements of r raised to power n are real, and that is why norm of x must be greater than 0. And we have proved here norm of x greater or equal to 0. Greater than is proved. Now we have to prove if the element x equal to 0, then what has happened? Norm of x equal to 0 if and only if I from 1 to n xi square root equal to 0. That equal to 0 if that is equal to 0. Now it is 0 if and only if the inner elements of the square root of any number is 0 if x equal to 0. If x 0, then the square root of that is 0. Here we have to prove which is equal to 0 if and only if the inner element equal to 0 I from 1 to n xi square equal to 0. It is 0 if and only if xi equal to 0, where xi equal to 0, that means x equal to 0 because x is equal to x1, x2 up to so on xn. So the first condition is satisfied, hence we can say that n is satisfied. Now for the second condition of a of x norm, which is equal to I from 1 to n a of xi square root. Now taking a as common. Now if you take a as common, then a square is cancelled with the square root, and it becomes mod of a from ai from 1 to n xi square root. Now that is x norm. That is x norm because we have defined which is equal to x norm. So we can put here I from 1 to n xi square is equal to x norm. So n2 is also satisfied. For the third condition, x plus y norm, which is equal to I from 1 to n xi plus yi square and square root. Now from the Minkowski inequality, I from 1 to n xi square root plus I from 1 to n yi square root, you can put if you expand expand xi plus ya modulo, then it becomes less or equal to I from 1 to n xi square plus I from 1 to n yi square from the Minkowski inequality. Now that is x norm and that is y norm. So x plus y norm must be less or equal to x norm plus y norm. So all three conditions, and one condition and two condition and n3 condition is satisfied, and thus we can say that r raised to power n with the norm defined by Starek, under the norm defined by the Starek, is a norm linear space. I hope so students you easily understand the example of the norm linear space. If the video is good, then make a comment and like my channel. Thank you.